This is the 10th lecture in this course on computational commutative algebra. So now, in this lecture, we look at versions of Nullstellensatz. So recall what we call the weak Nullstellensatz. So throughout this lecture again, sorry for not saying this again, K is a field and R is a polynomial ring in some finitely many variables over K, and I is an ideal of R. Okay. So with that notation, assume K is algebraically closed. Okay. Then V of I, that is the set of points in K to the n that vanishes at where every element of F vanishes, is empty if and only if I is the entire ring. So this is one version of the Nullstellensatz. So we will do another version. So let's write down another version. So I'll just abbreviate as NS for Nullstellensatz version 2. So this might look completely unrelated to the earlier version, but we will see that there is some connection. So let's again, assumption is the same, on K is the same, K algebraically closed. Let M be a maximal ideal of R. Polynomial ring in n variables x1 through xn. Then there exists a point in Kn such that M is the ideal generated by x1 minus a1, xn minus an. Okay. So let's think about this ideal for a minute. Okay, so we will prove that the weak Nullstellensatz that we defined here, that we recall here, something about the variety of an ideal being empty, is equivalent to the statement, although the way it is written, they look very different. So let's try to understand this ideal here, this ideal x1 through xn, just to understand where this ideal comes in. Okay. So remark, let K be any field not necessarily algebraically closed, and R again polynomial ring in n variables x1 through xn. Then, sorry, before one more piece of notation. Let A1 through AN be inside Kn. Then, the ideal x1 minus a1, xn minus an, the ideal generated by these polynomials, is a maximal ideal. I'll explain it in a minute. Let's go back to the statement of the theorem. In the theorem, it says that every maximal ideal looks like this. Here we are over an algebraically closed field. Here we are saying that over any field, this is a maximal ideal. And why is that so? Okay, so let's understand why. Why? Okay. So if we want to show that something is a maximal ideal, we can just show that it is a kernel of a map to a field, a surjective map onto a field. In other words, the ring modulo that ideal is a field. Okay. So let's say A underscore denote this point, this n tuple. Okay. And let me write EV, this is for evaluation sub A, evaluation at A. This is a ring map which goes from R to K, in which a polynomial in the x's gets evaluated at that point. So this is xi goes to ai, and constants go to constants. Okay. So this is a ring homomorphism. Please check that. Okay. If you take any of these elements, it is inside the kernel. Xi minus ai belongs to the for all I. Okay, so that's one observation. And a constant polynomial, so this is the first observation, for all k, for all alpha inside K, which is a sub ring of R, if you evaluate alpha, so alpha defines the constant function on Kn. In other words, it doesn't matter what you where you evaluate it, you would get alpha. So is surjective. Therefore, kernel of is the evaluation, sorry, not A alpha, evaluation at A is a maximal ideal. Okay. And what we will show is that it is the ideal generated by these linear polynomials. Okay. So, claim kernel of evaluation at A is generated by x1 minus a1, x2 minus a2, xn minus an. Okay. So now let's ask why this is true. So we already observed, so this is the proof of the claim. Okay. We already observed that this inclusion is true, that each one of them is in the kernel, so the ideal generated by them is in the kernel. Okay. So now what we want to prove is the other way around. Okay. So let f of x1 through xn be in the kernel. Okay. So write f as a polynomial in the last variable fi, x1 through xn minus 1, xn to the I goes from some 0 through d. Okay. Just as a polynomial in the last variable. Now, consider f partially evaluated at an. Okay, just let's go back. This is just expression of f. Now we are just evaluating it here. Okay, so this is take the difference, so this is the polynomial in which all of them are variables, and this is the polynomial in which the last variable has been evaluated at an. Okay. So this is just fi of the first n minus 1 variables, okay, times xn to the I minus an to the I, but this term is divisible by an to the I. This is divisible by xn minus an. Okay. Therefore, this element is inside the ideal generated by xn minus an. Okay. And we can repeat this. Okay. Now evaluate this polynomial. Okay. So let me just do it one more step. F x1 through xn minus 1 an minus through xn minus 2 an minus 1 an. So we are just evaluating it at one more step. Similar argument as above. So we can express this as a polynomial in these many variables with the variable xn minus 1 that we are substituting, and this is the ideal generated by xn minus 1 minus an minus 1. Okay. So therefore, okay, so repeat. So therefore, we will get that f x1. So let's put these two things together. F x1 through xn minus f x1 through xn minus 2 an minus 1 an isn't the ideal generated by xn minus 1 minus an minus 1 xn minus an. Okay. And now repeat this to conclude that f x1 through xn minus f of a is in the ideal generated by x1 minus a1 xn minus an. x1 minus a1 xn minus an. Okay. But notice that this is 0. This is the thing since f is in the kernel of the evaluation map. Okay. So that proves that kernel of the evaluation map is inside the ideal generated by x1 minus a1 dot dot xn minus an, and hence its equality here. Okay. So this is the remark that over any ring, ideals such as this, over any field, ideals such as this are maximal ideals. The content of the version 2 of the Nullstellensatz, is that over an algebraically closed field, every maximal ideal looks like this. Okay? And let's just make one more remark. Another remark. If K is algebraically closed, then every maximal ideal of Kx in one variable is of the form x minus a for some a. Okay. So what the Nullstellensatz, the version 2 of the Nullstellensatz does is to generalize this statement to larger number of variables. Okay. And this is proved because how does one prove this? If a maximal ideal, then it has to be generated by an irreducible polynomial, and if it's any polynomial in over k splits into linear factors, so irreducible polynomials are precisely the linear polynomials, and that's okay. So now let's so now so any proof of any version of the Nullstellensatz requires considerable amount of work, and for this course we will postpone the proof to a later stage where we will prove this version 2 that we just stated. Okay, that will come after we discuss integral extensions and method normalization lemma. One can directly prove the weak Nullstellensatz using elimination and resultance. There are other proofs of stronger statements from which these two will follow. So what we will do today now is to prove that the two versions that we stated, what we call the weak Nullstellensatz, and which is about the emptiness of V of I, and the version 2, which is about maximal ideals, they are equivalent to each other. That we will prove, that we will see now. The proof of version 2 will be given later, so that would establish only then we will have proved Nullstellensatz. Till then, however, we will continue using them. Okay? It is just that we postpone the proof till we develop sufficient techniques to prove it. But one should not wait till that is done to see how it's applied. Okay? So now, proof of Nullstellensatz version 2, which is the statement about maximal ideals, assuming the weak Nullstellensatz. Okay, so we will assume the statement about the emptiness of V of I and prove this. Okay. So what do we want to show? So let M inside R be a maximal ideal. Then M is not R by definition. Therefore, by weak Nullstellensatz, V of M is not empty. Okay. So take a point. Let A, which is A1 through AN, be inside V of M. So now let's look at, so we know that M is inside V of M. Sorry, it's not M. Okay. Okay. So let's consider what is the set of polynomials vanishing at that point. Okay, so let's go back here. What is okay? So now we want to look at this as a variety. Okay. So this singleton point inside Kn is a variety. Now we talked about the ideal of a variety, the set of all polynomials that vanish in that on that variety. Okay. So let I. Okay, so this is a variety. Okay. Let I denote the set of all polynomials that vanish on this set. In other words, that vanish at A. Okay. So then we observed the following. Then x1 minus a1 xn minus an is inside I, okay, and the constant polynomial 1 does not vanish at that point. So this is not equal to R. Okay. This is a maximal ideal that we proved. Any such ideal is maximal over any field. This we proved in the remark. Okay. So therefore, this must be equality here. So let's go back what this ideal is. So this is the ideal. This is the set of all polynomials that vanish on that at that point. Okay, so this is the observation that we need. So in particular, because since this point A is inside V of M, M must be inside I. Let's just think about it for a minute. M is some ideal which some collection of polynomials which vanish at A. I is the set of all polynomials that vanish at A. Therefore, M must be inside I. But again, this is, remember, this is equal to x1 minus a1 xn minus an. Okay. Again, this is maximal, meaning not equal to the whole ring. This is also maximal. But maximal is a property under containment, and this cannot be a strict inequality then. This now implies that M equals x1 minus a1 through xn minus an. Okay. So this proves the version 2 of the Nullstellensatz from version 1, which was the weak Nullstellensatz. Okay. We can quickly take a look at a Macaulay-2 example, which shows about this just to see that it's a maximal ideal. Yeah. So we define a polynomial ring in 3 variables, x, y, z. We map from R to Q. So this says x goes to 1, y goes to 0, z goes to 2. So it's evaluating a polynomial at 1, 0, 2. But then Macaulay-2 throws up some error. That's because in order to compute these things through algorithms, all these rings must have a certain structure, and in this case, QQ is not doesn't satisfy that. So it has to be some algebra where there are coefficients and then there are generators, and QQ is not defined like that in Macaulay-2. So one must be wary of these issues. So the way I want to get out of that is just define a map from R to R itself. So remember, Q sits inside as the subring of constant polynomials. So if you map like this, the image of this map is actually Q. Okay, that's because these are constants. Okay. So this is indeed doing the same map as earlier, and if you ask for its map, now the algorithm is able to run and it will produce what is expected: z minus 2, y, and x minus 1. Okay. Okay. So we will prove the other direction also. So proof of the weak Nullstellensatz, assuming the Nullstellensatz version 2. So this is a description of maximal ideals. This is the description of V of I. Okay. So what do we have? We have an ideal I inside R. Okay. So we have this. Okay. So what do we want to show? V of I is empty if and only if I is R. Okay. So one direction does not need anything. I mean, this is automatic. If I is R, I equals R, then there is no point at which every element of I vanishes. The constant polynomial, the non-zero constant polynomials won't vanish anywhere. So it is here that we need. Okay. So I is not equal to R. We assume that if I is R, then there is nothing to prove. Now we assume I is not equal to R and then prove that this is not empty. Okay. So assume I is not equal to R. Then, so remember that R is a Noetherian ring that we have proved. Okay. Okay. Then the collection of ideals J such that I is contained inside J and not equal to R is non-empty. Right? For example, I itself is inside here. Okay? This implies that lambda has a maximal element. This is one of the characterizing properties of Noetherian rings. Every non-empty collection of ideals has a maximal element. This implies that lambda has a maximal element. Let's call it M. Okay? As such, it is just a maximal element of lambda. However, because what lambda is, M is a maximal ideal of R. So remember that the word maximal element, this refers to a maximal element in this poset. Here it is a maximal ideal. Okay. So write M, so this is the hypothesis, x1, M can be written as this way. Okay. So then I is inside M. Then again we can show that this is the kernel of the evaluation map at A1 through AN. So therefore this implies that f of A1 through AN is 0 for all f inside I. In other words, V of I is not empty. Okay, so that's the end of this.